color components. So here's some light, here's what that spectrum would look like, and then if you were to plot wavelength of the light versus intensity, it would be this kind of black body spectrum here. And so there's going to be a peak where the source emits the most light, and then it tapers off. If you happen to put a cloud of some sort of gas in front of it, what the cloud's actually going to do is it's going to absorb some of the light and re-emit it. And so if it re-emits it, then the spectrum would look like this here. And it's just peaks at certain places, and we know that if there's a peak at this place, then that means it's this molecule, and if there's a peak at that place, that means it's that molecule. But also, if you were looking through the cloud to look at the light, you would see this spectrum minus that spectrum, which equals that one. And this is kind of the shape that we're going to be looking at tonight. All right, so there were 3 moon missions. They were the Indian Chandrayaan-1, there was Deep Impact, and then one that I'm forgetting, LRO, Lunar Reconnaissance Orbiter, and they all detected hydration on the moon. And they did that through spectroscopy. So here are some spectra. See, there's a dip here. That is where something is absorbing, and so we don't get that light, it's re-emitting somewhere else. And so this feature here is that the wavelength is 3 microns, and that is indicative of some sort of hydration. Chandrayaan plotted, they mapped the moon for the strength of this feature, and you can see that this is longitude and that's latitude there, and on the equator, there's not that much water or hydration, and then as you get towards the poles, there's more and more and more hydration, which is why we thought that at the bottom of the craters is where all of the water is. And it's interesting to note that all these yellow dots are the Apollo landing sites, and pretty much all of them landed in dry places. So a lot of the samples that we got back were dry. The issue with this particular absorption band in the spectrum is that it can't distinguish if the hydration is caused by molecular water, H2O, or hydroxyl or some type of hydroxyl species, OH. The feature is caused by the symmetric and asymmetric stretching of the OH bond in a molecule. And for those of you who didn't pass chemistry like I didn't, this is a nice diagram to show you symmetric stretching is when they both move the same way. Asymmetric is when they move different ways. And so the 3 micron band can't distinguish between those two. But there's another band at 6 microns that's uniquely caused by molecular water. And that's the bending of the H atoms around the O atom. Yeah, I didn't do good in chemistry. Chemistry does suck. Study physics instead, kids. Yeah, OH can't do that. If it tried to bend, it would actually just spin in a circle. So, awesome. Let's just observe the 6 micron feature. Easy peasy lemon squeezy. No. So, on Earth, we have this really cool but really horrible thing called atmosphere. And so what it does is it blocks most of the wavelengths of light on the electromagnetic spectrum. So this here this is a plot of all of the different wavelengths of light. This is over here is UV, and then you get to visible, and then infrared and radio, which Tracy likes, and then more radio, I guess. So basically, if it's brown, you can't see it. So you notice this rainbow here. It's nice and opposite of opaque, transparent. To us, which is why our eyes actually adapted, because this is the wavelength of light that the sun peaks in, and so that's why our eyes adapted to see that particular wavelength of light. Radio is also wide open. That's why radio telescopes can observe during the day and at night, all the time. That's why they're so awesome. The infrared here, as you can see, there's these giant bands of atmosphere just getting in the way. And particularly at the 6 micron region, it's right in the middle of that band there. So what do we do? If anybody wants to give me a couple $2 billion to build a space telescope, I'll take it. And at the time of this, James Webb was still on its 50th cancellation, so that wasn't an option either. So instead, we used SOFIA. SOFIA is the Stratospheric Observatory for Infrared Astronomy. It's basically a Boeing 747 airplane, and they modified it. In the back of, there's like this little door, and there's a 2.5 meter telescope inside of it. And so they open the door and they observe, and it's awesome and cool. And in particular, we used the forecast spectrometer, and that's that right there, and that's me. And so that creates spectra. It takes the light in the infrared and it splits it up into different wavelengths. Oh, and SOFIA can fly above 99.9% of the Earth's atmosphere. So it's like going to space, but not really. A lot cheaper. So we use SOFIA and the forecast spectrometer to measure the strength of the 6 micron feature. And so here, everybody get ready, this is Moretus crater. It is a crater that we can see from, it's nothing really special about it, but I put a little box around it. And so we took a bunch of spectra at this crater, and and here's what we see. This is a bunch of different spectra next to each other, and you can see a nice pretty peak around 6 microns. That's water. And so what we can actually do is there's laboratory spectra that people got glass from the bottom of the mid-ocean ridge, and then they measured the strength of the 6 micron feature and then plotted that versus amount of water, essentially. And so we can take the strength of all of these features and convert it to abundance of water. And so we find from all of our observations of Moretus crater, we find abundances between about 250 parts per million. Now, what does that mean? Because that's not like, is that like a swimming pool? What's up? The Sahara Desert has 100 times more the amount of water than we detected on the moon. So yeah, if you send an astronaut there, he's going to be thirsty. Which is why we decided that we wanted to make maps of the moon, and then we would know, like, oh, here's this future space mission and we need a bunch of water. Let's land here instead of here because here has no water because SOFIA told us that it didn't. So basically we make maps, we take a bunch of spectra and we line them up next to each other. That's what this left image is showing. Each of those little lines is one spectrum. And we literally just like open up Microsoft Paint and put them next to each other. And so you can actually see like topographic features here, right? There's Moretus crater. And you can see it. The thing that's flashing on is our actual spectral measurements. And then here, it's more orthographically projected onto the moon. Here's the South Pole. Here's the equator. And this is a plot of emission peak height, where the strength of the feature, lighter is higher. So we can see it's a little bit darker up here, and it gets lighter as you move closer to the pole. So that's kind of what we saw from the Chandrayaan images from the 3 micron spectroscopy. Yeah. Okay, so we can make maps. We're awesome. Go us. What now? These are the big questions that we're trying to answer. This is a whole giant project that I'm a part of. And so, first question, what is the origin of lunar water? Did it come from like asteroids colliding into the moon? Was it there when the moon was formed? What's going on there? How does it vary across the surface? Is it uniform everywhere? Is there more at the poles and less at the equator? I don't know. Can it move around? If it gets really hot, is it going to sublimate the water ice and cause it to, hop around or maybe just evaporate into space completely? And how is it stored? Is there like a lake or an ocean or something, or is it just little tiny particles on the surface? We don't know. Let's find out. There are 3 reservoirs that might host water. The first one is water that's absorbed on the surface, silicate surfaces. And so basically what happens is there's a bunch of hydrogen on hydrogen on the surface of the moon. And if micrometeorites come in or something, or solar wind, that's just a bunch of hydrogen particles. They're going to combine with the particles that are already on the surface, and they're going to create water molecules. And if it's just chilling on the surface, then when it gets really hot, like at lunar noontime, then those particles are going to sublimate and kind of hop around on the surface. And so if this is the case, we're going to expect that, at nighttime we're going to see a lot of water, and then at noon we're going to see less water. The second one is if you have water that's underground, kind of trapped within grains or inside of silicate glass. And so if any of y'all ever saw Sweet Home Alabama, one of my favorite movies, what's-his-face always went to the beach when it rained, because when lightning struck the sand, then it created glass sculptures. And same thing can happen on the moon. Micrometeorites come in, and if the energy is so large, it can actually turn the impact area into glass beads. And if the impactor had water on it already, like a comet or something, then that's actually going to get trapped into the glass. So that's really cool. And because it's trapped inside of glass or within grains, it can't sublimate. And so we wouldn't expect any variation with time of day. That's whatever, it's going to be the same. But we would expect a variation with latitude. Because of what we know, there's some other people somewhere else studied the amount of micrometeorites on the moon, and they found that there's more impacts on the equator than there are at the poles. So we would expect a variation following that general trend. And then the third reservoir is going to be water that's indigenous to the moon. And so that's if you had, when the moon formed, we think it's a giant impact. If there was water included there, that's all going to be sequestered in the mantle right now. And so if you have a thing like a volcano that brings mantle material up to the surface, or like a central peak of a crater, that's mantle material that's at the surface. So if we see water there, then that means that it's indigenous to the moon, which is really cool. And so we designed our whole observation program to kind of test these three theories. And so these are 2 different nights of the moon. These contours are telling you temperature. And so the red contour is cool, it's 6 a.m., the sun just rose there. 12 p.m. is noon, it's super duper hot there. And so if we observe the same spot on the moon at 2 different temperatures, here's green and here's purple, that's hotter. If we see a change, if we see that there's less here than there was there, then that goes with number 1, that there was water on the surface, it's sublimating. If we observe a bunch of points along one temperature and different latitudes, and we see a variation there, then we know that the water's in the impact glass or in the grains. And then if we see, this is Copernicus crater. It has a very, very prominent central peak, which is a bunch of mantle material. If we see stuff there, water there, then geologic features, indigenous moon water. And so this is actually all of the observations that we had. Sophia is very dead. But this is what we got before it ended. Each of these little blue squares is a map, like that one that I showed earlier. So we actually got 2/3 of the near side of the moon, which is kind of awesome. And you can see that we tested all 3 of these things. Here is a spot that we observed 4 different times at different times of day. We're looking at the variation, or if there's water on the surface. Here's Copernicus crater. We're looking for geologic features of water. And then here's, latitude runs that we've done. So, so far, all we've actually published is this little area right here. So there's going to be a lot more coming from this project soon. But here is what we've seen so far that I'm not supposed to tell you, but I'm going to, because I don't work there anymore. We're not really seeing variation with time of day. Yeah. Weird. We are seeing a variation with latitude, but it's not following what I told you that it's more at the equator and less. That's not happening. We're seeing that there's less water at the equator and more towards the pole. So what's that about? I don't know. I don't work there anymore. And we are seeing water near geologic features that contain mantle material, like craters. But most of the moon's surface isn't covered in mantle material, and so that's, kind of like less likely the source of most of the lunar water. And so what the last paper that we had concluded was that water's trapped in impact glass, just like Sweet Home Alabama. And yeah, here's a summary that I wrote. We're mapping water on the moon with the 6-micron feature in Sophia. Sophia's dead, but we have the data, and that's all that matters. We see evidence of variation of water abundance with latitude. We saw that there was more towards the pole. And with topography, we saw that there was kind of like, I didn't actually say this because I forgot, but if you have a mountain, the side facing away from the sun has more water than the side facing towards the sun. That makes sense, and that's cool. Water most likely resides between lunar grains or trapped in impact glasses, and we have a bunch of observations that we're working through right now. And here's the paper if anyone wants to go read science on a Wednesday night. Yeah.
All right, thank you. That was very, very cool. Woo!
Yeah.
All right, here we go. Here's a good question. First question here. Let's also, can we put the number up for people to text? I'll say it out loud one more time, 954-871-5620. Oh, damn it. Can Sophia measure water trapped in silicates?
Yes. In fact, that's going to be the next paper.
Ooh.
Yeah.
All right. How did it die?
NASA cut all of our funding. And so Sophia is no longer, it had its final flight. It was very sad. Everyone cried. I was hired 1 month before.
Repeat the question for people online.
She asked if it was a surprise that Sophia was dead or if it was, it was the Biden administration. No, I was hired 1 month before and along with like 10 other postdocs and then, yeah. Big surprise.
I think appropriate today, actually, just a quick thing, Boeing tweeted out a photo of their last 747 leaving the factory. The Queen of the Skies is end of an era.
I'll tell you what, 747s are awesome. In the bathroom, it had an ashtray.
Yeah, so that's one of the questions. What was the experience like on Sophia? Yeah.
Oh boy, I could talk your ear off about that. It's awesome. You get there around 6 p.m. You don't go home until like 7 a.m. It's like a 12-hour flight, but you don't go anywhere. So imagine that. But you can walk around, and there's coffee, and you can go hang out in the cockpit all you want, and the pilots like to talk to you.
I can imagine. Just not going anywhere must be tiring.
Yeah.
All right, keep those questions coming in, and I guess if anybody has questions in the room and you want to raise your hand, you can. I like this one just quickly. This one's funny. Whoever thought of this, you may be a comedian. If you moon someone on the moon, do you earth them?
I'll tell you what, I'll be the first one to try it.
Tracy.
So that was awesome. Question on with the water variation that you are seeing, even though it's not lined up with like the micrometeorite distribution, it does line up with temperature. So does that tell you something that doesn't necessarily, or does it complicate the story, I guess?
Both. It kind of tells you that temperature is more important than, time of day, but time of day is just localized temperature. So you're looking at the same thing twice. I don't know if that was a good answer. How much does the solar wind play into migrating molecules across the surface of the moon? A lot. So solar wind it's high energy hydrogen and kind of helium atoms essentially. And so anytime you have a burst of energy, something can move. And it's happening all day, every day. So it's not going to be enough to kind of like send a particle really, really far. I think it would only go a few kilometers. Tracy doesn't know either. But it definitely plays a role. And that's something that I don't think we really understand super well yet. Yeah.
Have you all looked at the Apollo samples versus the spectra to see if they match?
Have we looked at the Apollo samples versus spectra to see if they match? Or changed, yeah. Yeah, so the short answer is no. Long answer, Apollo happened, it was the 60s and the 70s. I wasn't alive, but I hear it was crazy. And a lot of those samples weren't really well preserved. And so there's like a lot of spurious stuff. And so we haven't looked into it just because it's going to be difficult to kind of discern, like, is this real? Is this what was actually from there? Or was it like, it's 50 years old? Did something from a lab get into it? Yeah.
I'm just going to do a cool plug where not only that, though, in the labs at Southwest Research Institute, they have Apollo samples, and they dose it with water and see what that looks like so they can compare it. But that's mostly done in the UV right now, but they can also do it in the infrared. So there are ways to do it.
Yeah, there's definitely ways to do it. It's just our team is 4 people right now. And so, we're not really, there yet.
I don't have anything else on the phone, so if y'all want to... Oh, wait.
Is it about mooning again?
Well, if there was a crater full of water on the moon, were aliens... I think it was phrased wrong, but were aliens having a pool party?
Well, water on the moon's probably ice, so maybe an
you know.
ice skating party?
Oh, there you go. They play hockey on the moon.
No, we don't do that.
Aw.
This is America.
Hey! Oh.
When you're dealing with those 3 and 6 microns,
Yeah.
how do you tell from Earth or high up in that atmosphere, looking that far away? How can you get detail with the wave, like in your
Yeah.
instruments? How can you tell that that's not just a blip or some kind of?
Yeah. So basically, the more light you get, the more signal you get. So if you expose, if you take a picture with your camera and you leave the shutter open for 10 seconds, it's going to be completely white because you got way too much signal. But in space, if you leave it open for 10 seconds, then you got just enough signal. And so basically, you integrate your exposure time long enough that your signal is going to be high enough compared to the noise that you know that your detector has. And that just has to be bigger than the thing you're looking for.
All right, we'll go with this one. Last question. How deep into the lunar soil was Sophia expected to have been able to detect water?
I should know this. It's meters? It's like microns. So the electromagnetic spectrum, spectroscopy. So the UV and stuff does like surface level, and then the longer wavelength you get, the lower into the depth you get. So infrared is going to be like microns, 10 to the minus 6 meters. Teeny tiny.
Thank you. All right, one more round of applause. And we will go on a short little break now for, is this the 5 or 10? 5? All right, oh wait, no, 10. All right, so 7:45. 7:45 we will resume. If you want to fill out the survey, you can. Be sure to order, don't crowd the bar, order from your waiters and waitresses in the room, and don't forget to tip them at the end of the night. And also come check out our merchandise at the table over there. We've got shirts, pint glasses, keychains, stickers, and lots more. So we'll see you in 10 minutes. Continue. Our next segment is our monthly Astronomy in the News, given by, as always, Caleb Guimar from a fellow student in the UTSA SWIRI Joint Space Physics Program, and he also is very involved with the UTSA Observatory. What's the name again of it? Curtis Von Jr. Observatory, that's correct. So give it up for Caleb.
All right, hello. Good evening, and I'll go ahead and get started with the astronomy news. So, first and foremost are our skies for December. So the star map that you see here is of the skies that appear around 9 o'clock p.m. throughout much of the month. We still have a very nice view of Jupiter. It will start heading over toward the western part of the sky. And of course, if you want to get a good look at Saturn, it is still there. At 9 o'clock, it's very, very low. But hey, you know what? We are during the darkest part of the year. So you can go out quite a bit earlier, probably around 6 o'clock, and you have a pretty dark sky, and you can definitely see Saturn. Still pretty high in the sky, just kind of shift everything over that way a little bit. Mars appears extremely nice right now, though. We are just past our closest approach with Mars for this year, and it won't be anywhere near that close again for really quite some time. We will have another close approach a couple of years from now, but it won't be quite as close as this one. So if you look almost right above you in the sky around this 9 o'clock p.m. time, you will have this really nice glowing kind of salmon colored star in the sky. That is the planet Mars. So do get a good look at that while it is up and nicely visible in the sky. Don't miss some of the deep sky wonders. Find a good clear sky spot and scan across the Milky Way with a pair of binoculars. There's a lot to see there, particularly the Pleiades, the Seven Sisters, a nice open star cluster right there, just forward of Mars in the sky, actually. So very easy to find that. It's a nice little collection of what appears to be about 5 to 7 stars with your own eyes without any magnifying equipment. But if you take a look at it with a pair of binoculars, you'll see several dozen stars scattered across that really beautiful field of view. There is a meteor shower coming up, a fairly nice one. The Geminids meteor shower peaks around the December 12th, 13th time period. The only thing is we have a really bright moon during that time as well, so that's going to kind of cut down the number of meteors you see. But nonetheless, so if you do look over toward the constellation of Gemini around that time of the month, and you're out in a nice dark sky, you will see quite a few meteors streaming away from there. It's one of those things where you kind of have to look up, and maybe every couple seconds or so you'll see something to shoot by. Now here's a very fresh story. It was just announced today. The discovery of what is called a kilonova, and not just any kilonova, but rather odd-acting kilonova. So about 1 billion light years away, a neutron-star merger happened. 2 neutron stars collided with each other. Normally, this results in what's called a short-period gamma-ray burst. However, this particular kilonova event resulted in what actually looked to be more of a long-period gamma-ray burst. So this is rather unusual behavior. At first, it was thought that this was a normal supernova event that would result in a long gamma-ray burst. But in this case, though, a little further investigation by the scientific team that made this discovery found that this was indeed actually a neutron star merger, and hence what's known as a kilonova. And so you can actually see the gamma-ray burst in this up-close image here. This is actually a combination of photography from the Gemini North Telescope and the Hubble Space Telescope. So very fascinating discovery from just announced today. About 1 billion light years away, so you're looking at that as it appeared about 1 billion years ago, all right? Now, there was a very interesting discovery announced using the James Webb Space Telescope mid-month, and that was the characterization of the atmosphere of an extrasolar planet, WASP 39b. That WASP stands for Wide Angle Survey of Planets, Survey for Planets, I should say. And going across the various spectral ranges provided by the instruments on the James Webb Space Telescope, they were able to not only characterize some compounds that had already been observed in this atmosphere by other observatories, but many, many more, including water, some signatures of sodium, definitely sulfur dioxide, carbon dioxide, a little bit of carbon monoxide. But basically, this observatory, this new space observatory, revealed this exoplanet atmosphere as never observed before, and revealed to be something far more complex than what really in many ways was previously imagined. And there have been more discoveries and great imagery by the James Webb Space Telescope, far more than what I have time to describe in this very short Astro News segment. So please go online, look for these images. They are phenomenal. You will not be able to stop staring at many of them. They are truly beautiful pieces of imagery, including just announced again just about a week ago, if I remember right, this really nice image of Saturn's largest moon, Titan, where you can actually see some of the albedo variations on the surface, possibly some of the features associated with the liquid methane lakes, and definitely some of the cloud features. So again, really, really awesome stuff from the JWST. But the biggest news recently, it launched. Finally. I told you, just wait, it'll happen. But no, it did launch, and it has been a truly phenomenal mission. It's worked out fantastically well. It is on its way back home now. It just made its last close approach with the moon a couple of days ago. This is a photograph of the lunar surface from that particularly close approach. But some of my favorite images are actually of the capsule as it was orbiting as farthest point from the moon. Very far distance, actually a record distance for a spacecraft designed to carry people into space. So you can see in this image that the moon actually appears to be really big in this picture, but that's because the moon's actually in the foreground. The Earth's way back there in the background. And another really nice image along that line, again from the return journey, not released too long ago, this image, showing the Earth is that crescent out there in the distance, and that really haunting view of the lunar surface. Just the stark contrast between light and dark on lunar surface is really amazing to see, no matter what. So a few things to keep in mind. Not quite as much coming up here very soon as I normally have, but again, do remember we have the solar eclipses coming up for the San Antonio area, not too far down the road. In fact, the annular eclipse, the one that you still have to have the solar eclipse glasses to really get a good look at, where the moon covers the sun, but not completely, that is coming up on October 14th of 2023. So we are less than a year out from that, in fact, so do bear that in mind. And then we've got a total solar eclipse, of course, coming up on April 8th of 2024. And then the Artemis 1 return will happen on Sunday afternoon, so definitely watch on the NASA TV feed online that Artemis 1 re-entry and splashdown. So that is astronomy news. Thank you very much, everyone.
Thank you again so much, Caleb. That's incredible. The to our next speaker, Dr. William Kosmann. Welcome. All right, here we go. Dr. Kosmann possesses 3 technical degrees: a BS from MIT in aeronautical engineering, an MS from George Washington University in system engineering, and a PhD from George Washington University in system engineering. Dr. Kosmann has worked in space system development or operations for 47 and a half years, including on the following projects: the US AFDMSP. What does that one stand for? It's a weather satellite. It's a military weather satellite. the Voyager Grand Tour of the Outer Solar System, the International Space Station, the Dawn mission to the asteroid belt, SWIRI's Punch heliophysics mission, the NOAA Space Weather Forward Observatory, and that will be the subject of this presentation, SWIRI's Solaris Solar Polar Mission proposal, and a whole host of other SWIRI space science mission proposals. So without further ado, here's Dr. Kosmann. And remember, the number is the same. And oh, and what's your drinking word for tonight?
Okay, so I'm going to mix it up a little. I'm going to have two drinking words. The primary one is CME for coronal mass ejection. The secondary one is UTSA for our honored guests in the corner. But I'm not going to use the secondary one very often, probably just once. So up or down, let's see here. That way. Yeah, I see the computer. Okay, so I got a tough act to follow. The first speaker was very energetic and upbeat and had a really wonderful topic to talk about, pools and ice hockey on the moon. I'm the exact opposite. This is going to be a talk about what happens when something very bad goes bump in the night. So my talk's going to be about the total destruction of civilization as we know it. Exact opposite of the first one. Okay, so a month ago, we had a speaker, a graduate student at UTSA, who talked to us about the Carrington event and the astronomer Richard Carrington, who noticed a very unusual thing in 1859. Okay, so in 1859, a giant CME came off the sun. About 17.6 hours later, that mass of stuff impacted the Earth. In 1859, it meant people as far south as Caracas, Venezuela, could see aurora at night. And the only electrical system in operation around the world, the telegraph system, had keys chattering very oddly with nobody pushing them, okay? This kind of stuff has been happening as long as the sun's been around, for the last 4.5 billion years. Stuff comes off the sun in all directions at all times. So what's different now? We haven't had one of these Carrington events since 1859. What's different now? Our entire civilization is based on electrical and electronic technology. And unfortunately, when something like a Carrington event engulfs the Earth, it does very bad things to electronics and electrical components. So last month's guest speaker from UTSA told us about two things that we could do to mitigate what happens when the next Carrington event hits. One thing we could do is develop electronics that would be immune to it. However, that's not cost effective. The second thing he mentioned was that we could predict when the next Carrington event was going to happen, except physics is not there yet, Tracy. So those first two things are out. But what our esteemed speaker from UTSA didn't talk about is that we're actually doing quite a few things to mitigate what happens when the next Carrington event hits. So that's what I'm going to tell you about tonight. So on the left, you see a picture from a coronagraph. A coronagraph is a visible light imager. It's a very specialized imager. It takes an image that's an annulus. It uses an occulter. So where is the laser? That guy, okay? It uses what's called an occulter to blot out the sun. When you blot out the sun, you can see the stuff that's coming off the sun. So this is what's known as a CME, coronal mass ejection. And, I don't know, maybe 2 days later, this mass of stuff hit the Earth, and this was the result. In 1989, Quebec, Upper New York, and parts of New England, electrical grid went down. No lights, no electricity anywhere for a couple days. That's what a small CME does. The next time we have a large CME, a Carrington event, okay? Lloyd's of London, who many of you have heard of, is an insurance conglomerate in London. In 2013, they wrote a report that estimated that the damage to the U.S. electrical grid from the next Carrington event would be somewhere from $0.6 trillion to $2.3 trillion. And it would take anywhere from 4 to 10 years to repair. So whatever part of the Earth that thing hits, imagine thousands of transformers just bursting into flames. And there's probably only a few hundred transformers sitting around in warehouses. When the whole electrical grid goes down, right, nobody can move, nobody can go anywhere. I don't know how you're going to get the transformers from where they're sitting in warehouses to where they need to be to replace the ones that blew up. So it's going to take quite a while if this thing ever happens. Quite a while to fix it. Oops, so that's the wrong way. Okay, so like I said, these things happen all the time. Here's one from 2017. This is a whoops. I don't know what I did. Made the whole thing go away. Okay, so this is a CME coming off the sun. There were actually a series of them, late August, early September. This is a coronagraph image of one of them, okay? And this is an article that was on CNN. It's a really fascinating article. If you're interested in this topic, look up this article from September 15th, 2017, entitled "Earth Dodges a Cosmic Bullet for Now." So a huge Carrington-class CME came off the sun, but it didn't come toward us. That's how we dodged the bullet. Oops, wrong way. Okay, so what happens when a CME hits our technologically based society? All kinds of bad things. So this is a graphical representation of parts of our technology that get messed up by the CME. Focusing in on just a few of them, we see that satellite operations are going to be all messed up. Any humans in space are going to be all messed up. Aircraft ops, all messed up. Power grid going down. GPS probably going down too. Let's just look at that, the GPS. What happens when GPS doesn't work anymore? No, it's much worse than that. That's the least of it. It turns out that GPS is the fundamental source of timing for almost all of our technological society. Anything that uses time to do anything gets that time from GPS. So when GPS goes away, the fundamental time source goes away. So stock market operations, banking operations, they all use time. When a transaction occurs, it occurs at a time. Done, gone, boom, doesn't exist anymore. Okay? So the power grid goes down because the transformers blow up. That's this quadrant. Transportation systems don't work anymore because their op centers don't work because they don't have any timing references. All financial operations are kaput because they got no timing references. All communication systems are kaput partly because the electronics got fried and partly because they got no timing reference. So that's just one little tiny part of what's going to happen when this happens now. So, what can we do that's useful about this? That's the rest of the talk, okay? So there's like 4 steps here. We can create contingency plans that allow us to save that which can be saved. We could practice the contingency plans so that we know that they work and we know how to put them into place quickly. We could place what we call a sentinel, which is a spacecraft with the right instruments on it, in the right place in the solar system so we get an early warning so that when the warning comes, we can execute the contingency plans and preserve all the stuff that we can preserve so what I've kind of alluded to doesn't happen. So the rest of the talk is that. Okay, so in 2015, the Obama administration signed two fundamental documents here. They are the United States National Space Weather Strategy, this one on the left, and the United States National Space Weather Action Plan. These two documents put the federal government into motion. They gave different agencies, different federal agencies, different roles, and started the creation of the contingency plans and the exercising the contingency plans, and gave NOAA the lead on putting a Sentinel into space, supported by NASA, who would actually build the spacecraft for NOAA. The whole thing got started in motion, but that's not that long ago. I'm going the wrong way. No, I'm going the right way. Okay, so we're up to the second bullet here. The first bullet, we got the federal government moving in the right direction, starting to work with industrial partners to create contingency plans that can mitigate the bad things that are going to happen when the next Carrington event occurs. So the next step is, once you have the contingency plans, you need to practice them so you know how to use them and implement them quickly, because it turns out when you put the Sentinel in the right place in the solar system, you still only get a 15-minute warning. So you got to act quickly if you're going to save stuff. Okay, so FEMA's got the operational lead here in making sure all this stuff works when we get the 15-minute warning. And FEMA, for a while now, years, has been working with the various electric utilities and various industries like the GPS, all the people that make and operate satellites, all the airline companies, anybody going into space, working up these contingency plans, practicing the contingency plans so we can actually do something useful when this happens. Okay, third bullet. We want to put a Sentinel in the most useful place to give us this 15-minute warning. So it turns out the right place to put a spacecraft with the right instruments on it is what's called the Lagrange point, L1. So if you have two bodies, say the sun and the earth, and one of those bodies is in orbit around the other, that automatically creates what we call Lagrange points, after the French mathematician Lagrange, who in the late 1700s figured this out. A Lagrange point is a point in space where the sum of the gravitational forces equals 0. It's a stable point. So the easiest one, so there's 5 of them. Anytime you have two massy bodies, one in orbit around the other, you have 5 little Lagrange points set up, and they're labeled here, L1, L2, L3, L4, and L5. The easiest one to understand is L1. This is the point in space where the gravitational pull of the sun is exactly equal to the gravitational pull of the Earth. Since the mass of the sun is so much larger than the mass of the Earth, that point is very close to the Earth and very far away from the sun. Turns out it's about 1 million miles away from the Earth, about 92 million miles away from the sun. Okay? So we want to put our Sentinel in that place. Because what happens when one of these CMEs, hey, somebody's awake. One of these CMEs comes off the sun, it doesn't do this. It kind of spirals out and does one of these and when it hits the Earth. But it still gets close to the L1 point before it hits the Earth. So if we put something right here in this nice little stable point, then it will detect and be able to measure the intensity of what's coming and give us a 15-minute warning. But that only happens if we have the right set of instruments on the Sentinel. So we want a coronagraph to take a visible image of what's coming, and we want magnetometers, a solar wind ion instrument, a solar wind plasma instrument to measure the intensity of this mass of this plasma that's coming from the sun and about to hit the Earth. I already showed you what a coronagraph image looks like. There's a coronagraph. Let me remind you that a coronagraph image looks like this. This is an actual coronagraph image. So we want to have one of those. We want to have a coronagraph on our Sentinel to take images of the sun, like 3 a minute, 24/7, 365. It turns out if you take 2 images of something that's coming off the sun, then you can determine the velocity vector of that stuff that's coming off the sun, which means you can determine how fast it's moving and the direction it's going in, and you can figure out if it's going to hit the Earth and how long it's going to take to hit the Earth. So for reference, the Carrington event was estimated to impact the Earth 17.6 hours after it came off the sun. That's the fastest event we know of. It's estimated that the slowest event, and the longer something takes, it is less intense it is, less energy it has. A slower event might take up to 4 days. So you got anywhere from 4 days to roughly a half a day or 3/4 of a day of warning from our coronagraph images that something's coming. And then when that something gets to the Sun-Earth L1 point, we can measure its intensity for the first time, because the coronagraph only tells us something's coming. It'll give us a good estimate of when, but it doesn't give us any idea of the intensity. So it's when the Sentinel at the Sun-Earth L1 point actually measures the energy of the various particles that are in this plasma that are about to hit the Earth. That's when we know the intensity, and that's when we know what to do, which contingency plans to actually implement immediately. So these are like, this is a kind of a design of what's called a compact coronagraph. The Punch mission, which is the Southwest Research's second mission where we're developing the spacecraft in-house, has a coronagraph as one of its 2 science instruments. So I'm very familiar with the compact coronagraph. I was the technical lead on that mission for the first 5 years of its existence. So it's basically, whoops, I did it again.
Technical lead?
Yeah, technical lead. Not the technical lead of this guy. So it's a telescope, and the light comes in this end, and there's the occulter that blots out the sun, and it acts just like a telescope. The photons it measures ends up in the detector. So these are called fields and particles instruments. This is an image of the Voyager spacecraft, but it's dominated by its magnetometer boom. There's a magnetometer here, a magnetometer there. Then there's these 2 in situ instruments that measure the actual intensity of the plasma that's about to hit the Earth. So, where have we been getting these coronagraph images? Because this Sentinel is not at Sun-Earth L1 yet. It's being built right now. It hasn't been launched yet. So it turns out, since 1995, when the SOHO spacecraft was launched, it had 3 coronagraphs on it, C1, C2, and C3. C1 failed in the first year. C2 and C3 still function. SOHO, the spacecraft, is working, and then C2 and C3 are working. So since 1995, we have been getting all of our space weather coronagraph images from SOHO. From a spacecraft and a set of instruments that were designed to last for 2 years. The entire world is getting its coronagraph images from a spacecraft and a set of instruments that were designed to live for 2 years. It's pretty sad. Now, there have been other Sentinels launched since then. Well, that's interesting. There's supposed to be an image right up here. I don't know what happened to it. It disappeared. Let's see what happens when I do this. There it goes. All right, so NOAA, it was designed by NASA, but it was launched. It was a NOAA mission. How many of you remember the spacecraft called GORSAT? When Al Gore was the vice president, he wanted to launch a spacecraft that had a camera on it that would take pictures of the Earth. He would nothing but take pictures of the Earth and beam them back, and kind of got roasted, probably on late night TV as well in the papers. GORSAT got repurposed and actually became the NOAA Discover mission, and it It was launched in 2015. It has the three fields and particles instruments, the magnetometer and the plasma and the ion instruments. It was launched to Sun-Earth L1, so it's doing that part of being our sentinel now since 2015. Part of the problem with Discover is it was launched in 2015 and it was designed to last 5 years, so we're already 2 years past its lifetime. So we're living on borrowed time with Discover like we're living on borrowed time with SOHO. There are other coronagraphs and ion and plasma instruments on other spacecraft that can partly fill in. But what we really want to have is a spacecraft at Sun-Earth L1 with a coronagraph and with an ion and plasma parasensors and with a set of magnetometers on it functioning all the time. And we're not there yet. But what's going to provide all that is the Space Weather Forward Observer, SWIFO. So this is a NOAA mission. It's the follow-on to SOHO and Discover. It'll be the first time we've got our coronagraph and our fields and particles instruments all on the same spacecraft. Okay? It's going to launch with IMAP. It's a ride share on IMAP. IMAP is another major NASA mission, science mission, that's going to look at the outer part of our solar system. IMAP's the primary, SWIFO is the secondary, and it's supposed to launch in the first quarter of 2025. So we still got like 2 years and 3-4 months till we have our space weather sentinel in the place where we want it, and then we will be in position to get our 4-day down to 18-hour warning from the coronagraph, and then our 15-minute warning from the fields and particles instruments, so that we can execute our contingency plans, turn stuff off, turn stuff around, so only a tiny part of what otherwise would be destroyed isn't destroyed and survives. Okay, so these are the goals. I worked in the SWIFO project office for a couple of years, was the lead for creating the Level 1 requirements document. So the goal of the SWIFO project is to maintain space weather data continuity by providing space weather observational data needed for the Space Weather Prediction Center to create useful space weather watches and warnings. The watch is the coronagraph image part that gives us the 18 hours to 4-day warning, and then the space weather warning is the 15-minute part, okay? So that breaks down into 5 objectives. Provide CME imagery from coronagraphs. That generates the space weather watches. Provide the in situ solar wind data from the magnetometer and the plasma and ion instruments. That gives us the space weather warnings, that's the 15-minute guy. Provide space weather observational data from 2022, this year, to 2032. They're not going to launch till 2025, so these numbers would change from 2025 to 2035. And oh, by the way, SWIFO is supposed to be an operational program. So there's going to be a SWIFO 1 designed to last 10 years, then there'll be a SWIFO 2 that's designed to last another 10 years, and it'll just launch to replace forever. So we'll always have a Space Weather Sentinel at Sun-Earth L1, which will give us the warnings we need to not go back to the Stone Age. Objective 4, be able to provide those warnings at least 98% of the time. And Objective 5, this is related to measuring the intensity of what's coming, and I'm going to get into this in the last slide. The people that do this for a living have set up five-point ranges. They go from 1 to 5. So the S range, S1, 2, 3, 4, 5. That measures an aspect of the intensity of what's coming. So this gets at our Sentinel at Sun-Earth L1 is going to experience what's going to hit the Earth, right? It can't be designed to work in and survive the worst possible storm that's going to come off the sun. It can only go up to some certain point, and so this objective tells you what our Space Sentinel has to survive when stuff is coming from the sun and about to hit us and do bad things. Okay, so ultimately the objective is to have a worldwide space observation set of platforms at Sun, whoops, I did it again, at Sun-Earth L1 and in geosynchronous orbit and some in polar orbit. And there's a whole host of countries around the globe that are collaborating, including a couple of bad ones, in this endeavor. And these are some of the missions that already exist. So we're not there yet. Maybe in the coming decades we will get to the point where we have a global initiative to be able to give us a proper warning for anything bad coming off the sun. Okay, last point. When the warning comes, the 15-minute warning, execute the contingency plans. So here's a little graphic I just mentioned about the scales. There's a solar radiation storm scale from S1 to S5. S1 is the least intense, S5 is the most intense. There's a G scale from G1 to G5 of geomagnetic storms. There's an X scale that goes from X1 to like X, I don't know, 50 or so, that measures the intensity of X-ray bursts coming off the sun. And then there's a radio blackout scale that goes from R1 to R5. And so when our Sentinel at Sun-Earth L1 measures the actual intensity of what's coming, we get the corresponding numbers on the various scales. And those scale numbers tell us which contingency plans to kick in now, what to turn off, what to turn away, so that it survives what's about to come. And my last slide is just an example of one of the warnings we get. So there is a thing called the Space Weather Prediction Center. It's it's a NOAA facility located just south of Boulder, and 24/7, they've been up for at least 10 years, maybe 15. 24/7, they're in the business of collecting the data they can from the various sentinels that are in the various locations in space and putting out these warnings. And this is an example of one of the warnings they put out. And you can see the three of the 5 scales I was talking about. The R scale, the S scale, and the G scale up here. Sorry, south of where? South of Boulder, Colorado. So that was it. I probably went over a little bit in time, but we are seriously working toward implementing a system that will warn us when the next Carrington event is going to hit the Earth, and with enough time to be able to turn the things off that would survive if you turned them off, but would blow up if you didn't. That includes electronics, transformers on the electrical grid. From the coronagraph images, if we got our 4-day warning, even if it's only a 1-day warning, we can shut down all the airline flights going over the North or South Pole. There's all kinds of things we can do to prepare for one of these when it hits, as long as we have the warnings. So we're working on it.
All right. Well, thank you. Thank you so much again. That was really interesting, and I don't want to imagine what if this machine breaks because of something hitting it. I assume that means uh-oh.
Yeah, it does. It means very bad uh-oh.
Yeah. All right, let's go. So yep, the number's up there for texting in your questions. How are atomic clocks affected by GPS outages?
I don't think the clock itself would be affected, but the electronics that are going to tell you time or the frequency at which something is vibrating would get blown out. And of course, those electronics need electricity to run, and if the grid's down, everything's dead anyway. But the clock itself, I don't believe the vibrating crystal or the vibrating molecule or whatever is the fundamental source of it. I don't think that would be affected at all.
Okay.
But all the supporting stuff would.
Let's see, our next question is, some of these, here we go. This is a good question. Can a Carrington event cause geological movement?
Not as far as I'm aware. It's not very massive. It's huge. It's a plasma. It's very energetic. It has effects mostly on electrical and electronic components. It's not like a meteor hitting the Earth, which is a massive body. This has some mass, but it's tiny compared to the mass of the Earth.
Okay, thank you.
So it doesn't have that kind of an effect.
Okay, would it be better, or would it work if you just go and sit in a Faraday cage? Would you fare well, you and your technology in your space, or no?
That's more of a question for a physicist. I don't know the answer to that question.
Yeah.
It's not going to affect us. It doesn't hurt us as human beings. I don't know if you put electronics in a Faraday cage that would ameliorate the effect or not. See, part of what happens is when this ionized plasma impacts the Earth, it sets up huge potential differences, which set up huge currents going in places where you don't want them to go, and that's what causes a lot of the damage. I don't know that a Faraday cage would affect that at all, because a lot of it is ground. They're ground currents when this ionized plasma impacts the Earth and hits the ground.
Okay. No. Yeah, it's not like that. So then a good follow-up would be pertaining to if you're on the night side at the time of this CME hitting the Earth, you really wouldn't be any safer than the day side.
No,
right?
you would,
Oh,
actually.
you would?
In fact, when these things hit, they tend to impact one hemisphere, whichever hemisphere happens to be facing the direction they're coming from, and don't tend to impact the other hemisphere very much at all.
Oh.
In fact, that's one of the things I didn't touch on. Our military has got all kinds of electrical and electronic components to the weapon systems, and if we haven't done the right things, then those weapon systems are going to be out of commission. So whatever hemisphere is impacted by a Carrington-like event is going to be more or less defenseless with respect to the other hemisphere for a while. Didn't get into that much, but that's another effect. He was buried in some of the charts, but I didn't emphasize it like I am now.
That's good to know.
I don't know. I think it's bad to know. Tell you the truth.
Well, I like this question. What would happen to personal medical devices? Like if you have a pacemaker or something, would you be?
Oh, it'd be fried. Electronics
fried?
would be fried.
Okay.
Absolutely. Oh, it's worse than that, though. There'll be no medical services because hospitals run on electricity. You couldn't get there because you can't go refuel your vehicle because all the gas pumps run on electricity. All the lights are out. You got no job. You can't do any financial transactions. No one's going to the hospital. No one can get there.
Yeah.
There's not going to be any doctors there.
So this contingency, if it works as you intended to, how much mitigation would there be as far as the timetable to full recovery?
So I'll just take one example. If you shut down the electrical grid deliberately, then the transformers aren't going to blow. So you shut it down, you get a 15-minute warning, you turn all the transformers off, turn the electrical grid off in essence, then bring it back up again 15, 30 minutes after the event has passed, and there's no damage at all.
Wow.
So some things there'll be no damage at all. Other things, all of our cell phones are going to get fried, right? We're not going to know. Even if we did, well, I don't know what we could do. Maybe go deep underground if we had the ability to do that. But personal electronics are going to get whacked. Residential electronics is going to get whacked. Industrial electrical and electronic components, they might be able to do a little more than we can do. But it's going to depend. Some things are going to be any damage at all. Other areas is going to be widespread damage.
Okay. Thank you. Question?
Yes, ma'am.
So, in your opinion, if we don't enough, and it isn't a problem that a fraction of 1% of the population even knows about the damage that could happen tomorrow? And when is the Hollywood blockbuster going to fall?
So that's three separate questions. So, first one was, have we done enough? Okay, we are relying on a 2 coronagraphs that were launched in 1995 and designed to last for 2 years for all of our coronagraph images to give us the half-day to 4-day warning that something's coming. So I don't think we've done enough, anywhere close to it. Second question, what was your second question?
Is it a problem that a fraction of 1% of the Earth's population knows about the damage that could happen? And if they don't know where to get warning information?
Well, I don't know that warning information is going to be broadcast to everybody. I tend to think that that's not a problem, because if this, there was this, I showed you a slide of a CNN article that was on the internet. Anybody that wants to look into this can. It's not like it's been withheld from people. No, it certainly hasn't been well advertised. I would tend to think if it was well advertised, that might generate some panic, some unnecessary and unneeded panic. And then on the other hand, what can you actually do about it as an individual human being? Not a whole hell of a lot.
Yep.
Yeah, it's got to be protected somehow. So I don't know. I'll give you a personal example that's kind of related to your second question, and that is, next year I want to install some PV arrays. I have a 12.5 acre farm in Northern Virginia, and I want to generate my own electricity. But I also want to do some research in what I need to do to make sure that the arrays, and more importantly, the control electronics, survive an event like this. So I haven't done that yet, but I'm hoping there is one or more things I can do beyond having a second set of electronics down in the basement somewhere that's hopefully protected.
Does that contingency plan go into effect or not into effect, but does it account for if it actually, 15 minutes is not enough time to shut down an election?
Yeah, it is. Oh, it absolutely is. If the warning gets out immediately and all of the grid operators receive the warning immediately, it certainly is. They practice this stuff.
But after the fact, because the rest of society would be in chaos.
Probably. In whatever hemisphere.
Have electricity in America, or grid doesn't mean they have electricity anywhere else, but everything else is started.
Yeah, well, if the,
Electric vehicles and everything else, we're just creating an equal disaster.
yeah, yep.
Well, I would say having electricity is better than not having electricity. Having lived in Texas 2 years ago, yes, I am encouraged with all of the stimulating conversation and questions, and thank you so much. But we do have to go on, so let's thank our speaker once again. If you have any more questions, yeah, go take a chat. And we are going to go on a little break one more time. And during this break, we're transitioning to trivia. So if you're going to stick around for the trivia, we're going to be passing out the sheets. And if you need a writing utensil, let us know as well. And we will be back in about 5 minutes. So 8:38. Thank you so much. And don't forget the merchandise, too.
He wasn't ready.
If you're ready to get started, say woo! Now we're ready. All right. Here we go. Huh? Odds? Oh. What do you want? Okay. As always, cell phones not permitted, because that would make it not fun, because we have wonderful prizes for you to win. So, make it fair. And please, to make it easier on us, just put down the multiple choice letter for the answers. That way it makes it quicker for us to grade and quicker for us to give you all your prizes. So let's get started with question 1. Where did Dr. William Kosmann earn his doctorate degree? A. George Washington University. B. Abraham Lincoln University. C. Theodore Roosevelt University. D. John F. Kennedy University. Or E. Barack Obama University. This one is easy just because logic. Everyone good? All right.
Question 2. Richard Carrington used sunspots to estimate the solar rotation rate. How long, on average, does it take the sun to make one full rotation? A, 1 day, B, 7 days, C, 15 days, D, 28 days, E, 365 days, or F, the sun just doesn't even rotate.
How sad. This one's a thinker, I'll admit. This one's a thinker.
Everybody good?
Speak up or forever hold your peace. So moving on. All right. Question 3. What type of solar eclipse is shown in the image below? A, a total eclipse, B, a partial eclipse, C, a penumbral eclipse, D, an umbral eclipse, or E, an annular eclipse. Caleb has mentioned this eclipse many times. Because it's going to, okay. It will occur here in San Antonio. That's all I know. Which type of eclipse is this? Ready to go?
Everybody good?
All right.
Question 4. What is the largest moon in our solar system? A, Europa, B, Earth's moon, the moon, C, Titan, D, Ganymede, or E, Enceladus?
This one's also a thinker. Everybody good? Question 5. A satellite that monitors space weather and generates warnings to Earth is called A Canary, B Probe, C Sentinel, D Alerter, or E Rover. This one is a memory recall question, so do with that as you will.
No hints. Everybody good? All right. Question 6. Who was the third person to walk on the moon? Not the first, not the second, but the third. Is it A, our very own Caleb Gamar? Is it B, Neil Armstrong, C, Yuri Gagarin, D, Charles Pete Conrad, where does that come from? Or E, Gene, I don't know if that's Cernan or Kernan.
Cernan.
Cernan. Not the first, not the second, but the third.
Oh yeah, Caleb Red Bull Gimar. That's true. I like this question. There's a few answers here that if you put them down, I'm just going to be sad.
Everybody good? Anybody need any questions repeated? Two? Can we go back to two, please?
Sunspots. Wait, no. Rotation, sorry. That's question 2. No. That you needed. So you're good? You're good now? Or
Anybody need another question?
the last? Okay.
Question
Are you good on
6.
2? Okay. 6 one more time. Everybody else is good? I don't have to go back to any others?
Going once. Going twice. Sold.
Come on, you all should know this. Bonus time. Bonus, get ready for the bonus. This one's a good one because name the 5 Mars rovers in any order. We threw a curveball at you. Yes.
Partial credit will be considered, I believe, in tiebreakers.
Yes.
If you get all 5, wow. I don't know if you should be doing this trivia, to be honest.
Or you're a physics student.
Exactly.
As always, if you're a physics student, you can give me your answer sheet, but you have to put down that you're a physics student on it, and you will be put in a separate pool for bragging rights only. No prizes, but bragging rights are worth more, especially in science.
If nobody needs no questions repeated, we're going to come around and collect the answer sheets and the pens as well.
Yes, don't forget the pens. We use them each time. And then we will take a quick break just to mark them up and get the answers. During the break, I want to remind you all, if you're checking out, be sure to tip the staff tonight. They've done a wonderful job. They do a wonderful job each time of helping, of serving us all. So treat them very kindly. Thank you. And, oh my, this is a disaster. There we go. The answers for tonight. Question 1 was about the, where did Dr. Kosmann go to school for PhD? And of course the answer is George Washington University. I think pretty much everybody got it right, so yes, you all have common sense in this room, at least. Question 2 is about the sun's rotation. Aaron?
The answer is 28 days.
Oh, shoot, we didn't.
For all you curious folks out there, the sun does indeed have a differential rotation rate. So different parts of the sun rotate at different days. That's why we included the on average. And if anybody had asked me, wait a minute, what about the differential rotation rate? I would have said, wait a minute, do you need to be doing trivia right now? Okay. Because you obviously know a little more than everybody else. Yeah, so different parts of the sun rotate at different rates. It's very, extremely complicated to even think about. I think so. I think the pole is like, I think it's a few days, if not almost, I don't want to say nothing, but like substantially shorter. I literally just learned this in one of my classes, so I should know this off the top of my head, but I don't. My exam was today, so we'll see how that goes, apparently. Pole is shorter. The equator is the most. 28 days is the equator. The equatorial region of the sun rotates at 28 days. It goes to about latitude of, say, roughly 10 to 20. And then above that, it gets shorter and shorter as you get closer to the poles.
It creates...
What I'm saying is, on average, the answer is 28 days.
It's right there. What it does, though, is I recommend, I don't know what you would Google, but there are cool animations of rotation of the sun rotating and with the magnetic field lines displayed, and because the lines, connect 2 points, and those 2 points rotate at different speeds, you get these weird twistings, and they look so cool. So I recommend...
And guess what happens when the twisting happens? That's when you get CMEs.
Yep.
Woo! Woo! We've come full circle.
So what type of eclipse is coming? Was the one that we showed and is coming to San Antonio? It is the annular eclipse. The annular eclipse, you see the sun is not fully covered. You get this beautiful ring, which you need the eclipse glasses for, by the way. If you are looking at this with your naked eye, you're blind. Yes, go to UTSA
Shameless
Physics
plug.
Department. They
There you
got
go.
really cool glasses. Yes. Woo, UTSA. Of course, we also have a total eclipse coming up, but this is not what this is. Question 4.
Question 4, I don't remember what it was. What is the largest moon? My guess was wrong. It is D. Ganymede,
Yep.
Earth's moon. I don't think I'm that far off. I don't think Ganymede is. So, kind of off.
We've got some big moons in the solar system, but think about just how big Jupiter is. So it kind of makes a little bit of sense that it can have very large moons. And Ganymede is one of them. That too.
Wait.
Yep.
I did not know that either. Wow.
Ganymede is quite large. Fun fact, Ganymede has its own magnetic field. That's how powerful it is. So, good, cool moon. Our next question was about what is the satellite that monitors the space weather? And that's, of course, the Sentinel, as given to us by Dr. Kosmann. So, that was a memory one. Question 6, the final question, was about the, oh dear. Well, we'll see. Who was the third?
Who was the third person? Not the first, not the second, but the third. It is indeed Charles Pete Conrad.
Caleb, where does Pete come from?
I would.
Oh my goodness. Okay. Could be the middle name. I don't know.
I expected in the astronomy news coming in February.
Yeah. We're going to learn all about Pete Conrad in the next. Caleb was fourth, yes. Yes, of course. All right, and then the bonus was about the 5 rovers on Mars. The names of each 5, and they are Sojourner, Spirit, Opportunity, Curiosity, and Perseverance. Perseverance, of course, is the most recent one, which was a big deal when it happened. Yes?
You missed Zhurong.
Uh-oh. That's right, yes. NASA rovers,
There we
NASA
go.
rovers. We are funded by NASA, so, we have an implicit bias. I mean, so now is the fun part where we get to give out prizes. So I'll start this time around because we did have a perfect one, but I said the physics students can't compete, but they do get bragging rights. As always, the graduate students got perfect.
Perfect.
Yeah. No, I'm just doing these for thank you. So thank you, grad students, for keeping the bragging rights home. Thank you. But we won this time. All right. We all have our days. Our third place winner tonight is not 1, not 2, but 3 people tied for third. Unfortunately, we talked about our tiebreaker was the bonus. These 3, not to call you out, you didn't get any of the bonuses. So, Yeah. But what you have coming your way is everybody on your team is going to take home an almanac, the 2022 Night Sky Almanac. Fun fact, thanks to Robert Reeves. Fun fact, 2022 is almost over, so enjoy it while it lasts. And each of you gets, because we talked a lot about the moon tonight, a special 10th anniversary LRO poster. Was celebrated in 2019, but it's still a momentous occasion. It's still going. It's still a good time. So our 3, we have Craters, CME, UTSA, Dream Team, and Jax and Annabelle. So everybody, come on up. Come on up, everybody. Claim your prizes. Congratulations. There you go.
Everybody, oh wait, Jackie, you get an almanac too.
Wait, do you have enough? Come see me after. We'll see. I'll see. I think we'll. All right. Congratulations again to the third place. Now in second place, winner tonight got 4 answers correct and 3 of our bonuses. The winner of what we have for second place is another one of those beautiful LRO posters, a LRO lamp sticker, a very cool design, another set of almanacs, a Europa sticker, and a cool Celestron thermos, once again courtesy of Robert. Alien probe. Oumuamua. Come on up.
We had to read it out.
It's his. The osmosis. So this brings us to our top prize of the night. And almost half of this stuff was given to us. We have we have the almanac again, the stickers, the poster, and a cool Celestron beanie. And like I said, most of this stuff was given to us by Robert, and it's going back to Robert. So that was tonight's trivia. Thank you all for participating. Oh, a bunch. You want to just... So we have a lot of almanacs left. 2022 night sky almanacs. Come on up if you want one. They're cool to have, even if the year is almost over. They have a lot of cool astronomical information in them. You can learn a lot from these almanacs. And be sure to look out for the 2023 almanac, which I'm sure will have. Thank you once again, everyone, for coming. It was a great time tonight. I know it was a little bit of short notice.
Give yourselves a
Round of applause.
And another special thanks to our two speakers, Dr. Kosmann, Dr. Arredondo. Woo!
Woo!
And we'll see you all in February. We're skipping January because everybody's going to be too hungover from the new year, like 2 days earlier than that. So we'll skip January. We'll see you all back here in February, first Wednesday of the month.
Yep. Everyone, safe, happy, and healthy holiday.
Yep. Thanks, everybody.